In our previous lecture, we saw how one deals with circuits that contain constant independent sources, LTI resistors and diodes. In particular, we obtained the IV characteristics of one-ports of some simple topologies that contain those three classes of elements. In this lecture, we will have some more examples. We'll continue with more examples, some of analysis, some of design. Okay. So let's start with an analysis example. Okay, so plot the IV characteristics of the following one port. So this is our one port that's composed of four components: a battery, a constant independent voltage source, two LTI passive resistors, and here we have a diode. Okay. And what we're asked is to figure out the relation in on the IV plane between voltage and the current of this one port. Okay. Now let's label the voltage of the diode as VD and let this be its current, IV. Okay. Now this diode, although it's a nonlinear element, it's a very simple nonlinear element in the sense that it either behaves like short circuit or an open circuit. Okay. And the condition that it behaves like a short circuit, that is the voltage drop across its terminals is 0, is that the current passing through it is positive. Okay. And the condition that it behaves like an open circuit is that the voltage across its terminals is negative. Okay. So therefore, we can do a region by region analysis and obtain and then combine the outcomes of our analysis into a single whole, and that will give us what we're looking for. Okay, so let's therefore consider both cases. The first case being the diode is behaving like a short circuit, which sometimes we call the diode is on, and in the second case, we're going to consider what happens if the diode behaves like an open circuit. So, assume that diode is like a short circuit. Okay. Now, this assumption comes under the condition that the diode current is non-negative. Okay, it's greater than or equal to 0. So, when the diode is on, we can replace this by just a wire, which is short circuit, so let's do that. So when the diode is on, we have the following one port. Okay. Plus minus V. This is I. This is the diode current. Now it's behaving like a short circuit, and the condition is that that current is positive. 3 ohms, 2 ohms, and we have 10 volts here. Okay. Now in this circuit, it's very straightforward to obtain the voltage current characteristics. Okay, so we're going to do that, and then we're going to translate this condition that the diode current greater than or equal to 0 into a condition either, well, condition in terms of the current or the voltage of the overall one port. Okay, so we're going to stick to the voltage, but we could have also done the current version. Okay, so when diode behaves like a short circuit, clearly this 3 ohm has no effect. This 3 ohm resistor has no effect. Therefore, this part is just a wire. Okay, just short circuit. So this voltage therefore equals the voltage drop across the diode, which is 0, plus the voltage drop across 2 ohm resistor, which is 2 times I. Okay, and then the voltage drop across the battery, which is automatically 10 volts. Therefore, V equals 2I plus 10 is the ID relation when the diode is on. Okay. So V equals 2I plus 10. Now, of course, this relation does not hold for all values of voltage and current. Okay, under what conditions that relation holds, we have to figure that out. Okay, and for that we're going to use this constraint. Okay, ID, the diode current greater than or equal to 0. Now check condition, or in other words, let's translate this condition into a condition in terms of, say, voltage, the voltage of the one port. Now, since here the voltage drop is 0, therefore the voltage drop across the terminal of the resistor is 0. That means no current is passing through the resistor. Okay, 0 over 3 is 0. That means this current, whatever it is, exactly equals the current passing through the ideal diode. Okay. So ID equals I. Therefore, V equals 2I plus 10. That we can write as 2ID plus 10. And then ID greater than or equal to 0 means that V must be greater than or equal to 10. Okay. So ID equals V minus 10 over 2, and ID greater than or equal to 0, which is our condition under which we can replace diode with a short circuit, implies V minus 10 over 2 greater than or equal to 0. So that means V greater than or equal to 10 for diode to be on. Okay. So we have figured out partially the voltage current relationship for this one. Okay, so we know what voltage current relationship, provided that voltage is greater than or equal to 10 volts. Okay. Now we're going to consider the other possibility where diode behaves like an open circuit, and then we will also obtain a relation and a condition, and then combining those two outcomes, we will obtain the overall, the global relationship between the voltage and current of the one port. Now, assume that diode is off, that is, it behaves like an open circuit, and the condition is VD, its voltage, is negative. Okay. So when this guy behaves like an open circuit, so to see better, let's quickly draw it under that condition. Okay. Now we're trying to figure out the voltage current relationship when the diode behaves like an open circuit. This is 3 ohm. This voltage drop is VD, and ID clearly is 0 in this case. This is 2 ohms and plus minus 10 volts. Okay. the voltage-current relationship is also obvious in this case. Okay. V, the voltage, equals this voltage plus that voltage plus 10 volts. This voltage is this open circuit 3 times I, and then this is the same current passing through 2 ohm resistor. So we have plus 2I, and finally we have plus 10. Therefore, V equals 5I plus 10 is the relationship between voltage and current. V equals 5I plus 10. Okay. Now we're going to figure out under what condition that relationship is valid. When diode is, so let's check the condition. Okay. So we have VT, this voltage equals 3 times I. Okay. And I is V minus 10 over 5, V minus 10 over 5, and then VD negative. Okay, so that's the condition under which this assumption, under which diode is off. Okay, so VD negative implies that this thing here is negative, and it means that V must be less than 10. Okay, V is less than 10 for diode to be off. Okay. So when V is negative, that's the IV relationship. Now combining this piece together with the initial piece, now we have the global picture, okay, or the global voltage current relationship between for the one port given. Okay, so let's put them here. Hence, the current equals V minus 10 over 2 for V greater than equal to 10. Okay. And the current equals V minus 10 over 5. V minus 10 over 5 elsewhere for V less than 10 volts. So that's the IV characteristic of this one port. Let's quickly visualize it. Okay. V in volts, I in amps, and this is the origin. Okay. So at V equals 10, we have a break point. Okay, let's say it's somewhere here. V equals 10. And when V is at V equals 10, the current is 0. Okay, so therefore we are on the horizontal axis. For V larger than 10, the slope is 1/2 moles. Okay. So here we're rising with slope 1/2 moles. And when V is less than 10, that is to the left of that vertical line that passes through V equals 10 volts, the slope is 1/5. Okay. Therefore it should be less steep. Okay. And the slope being 1/5, okay, 1/5, it means that this point here is minus 2 amps. Okay. So therefore, this here is the break point when diode switches from open circuit to short circuit. And at that particular point, it behaves both like an open circuit and short circuit. Okay. So ID equals 0 and VD also equals 0. Okay, so that's the IV curve for this one port. Now, incidentally, we could have solved the problem by the graphical method that we applied, that we talked about in the previous lecture. Okay. And one way to go would be, for instance, plot the IV curve of this piece, and then plot the IV curve of this piece here, and this one port and that one port. They are in series connection, and then add those two IV curves in series addition. Okay. For instance, we have VI. Okay. What's the IV relationship for this diode connected in parallel with the 3 ohm resistor? It's this. We know from the previous lecture. Okay, this is 0, and here we have 1/3 mohs for the slope. And then as for this guy here, we have a 2 ohm resistor, okay, which is a line passing through the origin with slope 1/2 mohs, and then to that we add a 10 volt voltage source, and adding a 10 volt voltage source in series with any one port, what it will do is it will shift everything to right 10 units. Okay. Therefore, what we do is we take our line passing through the origin and make it so that it passes through the point B equals 7. So we have something like this. Okay. 10, and the slope is 1/2. And this and that, they're connected in series. Okay. And then if you perform series addition of those two curves, what you obtain is the curve, slope here 1/2, and slope here is 1/2 plus 3. Okay. Now let's move on to our next example. Now this example, all our previous examples were examples of analysis. That is, given the circuit, obtain the IV curve. Now we will consider the other direction. That is, given the IV curve, obtain one port that generates that IV relationship. Okay. Now this, which we call synthesis. Synthesis is harder, sometimes much harder than analysis. The reason being that the answer, the solution, is not unique. There are many possible one ports that would generate the same IV characteristics. Okay. Now here we're going to be considering the synthesis problem or the design problem. Okay. Obtaining circuit from the IV characteristics. V okay. Here I0 1/R2. Here we have 1/R1 for the slope. Okay. And all these points belong to our curve. And we will now try to find a one port that contains ideal diodes, LTI resistors, and constant independent sources that would generate this IV curve. First thing we realize is that it has two break points. Okay. By break point we mean the point where the slope is discontinuous. Okay. So two break points mean that we need at least 2 diodes to realize our design. Okay, so we have 2 breakpoints. Therefore, we need at least 2 diodes in our circuit. Okay, now how we approach this type of problems is as following. So what we do is, given this final curve, we decompose this curve into simpler curves. Okay, so we're going to try to write this as some ID characteristics plus some other ID characteristics. And remember that we have 2 types of pluses, 2 types of summation. One is parallel summation, the other is series summation. Okay, and then by being careful about that, whether we're doing parallel summation or series summation, what we do is we combine the one port coming from one of the curves with the other one port coming from the other curves, either combine them in parallel or in series, and then we obtain the result. Now, suppose we decompose this thing into 2 curves. Okay, so this equals sum of 2 curves. Still, we don't recognize what that one of those curves, let's say, can be coming from. So what we do is we continue with the process further, meaning that curve we decompose even further, as we write it as summation of 2 separate IB characteristics. We do that on and on until we realize that curve belongs to some particular circuit that we're familiar with. And then once we reach that point, what we do is we combine all the pieces from bottom up and combine them in whether series and parallel summation, depending on how we decompose the curves, and we reach the final one port that generates the given IB characteristics. Okay, and remember that, as I said before, the solution is not unique. There are many ways to decompose a given IB characteristics, so that means there are many different circuits that would generate the same IB characteristics. Okay, so that thing we're already familiar with from Thevenin Norton equivalent circuits. Okay, we have Thevenin equivalent circuit and we have Norton equivalent circuit, and they both have, although they have different circuits, they both have the same IB characteristics. Okay, so this thing we can write as equal to something plus something else. Okay. Now this can be written as this guy origin, the slope is 1 over R1, plus this guy, slope is 1 over R2. Okay. So this plus that equals this. Now the question is, what do you mean by plus? That is, are we doing parallel addition or series addition? Remember that for parallel addition, what you do is, parallel means that they share the same voltage. You pick a voltage, okay, and you figure out the corresponding currents coming from each piece, and you add those currents, and that gives you the overall current here. If it's series addition, what you do is, you pick a current, okay, and then you figure out the corresponding voltages for that particular current, you add those 2 voltages, and it gives you the overall voltage in the original IB characteristics. Okay? And in this case, what we're doing is, if you want this plus that to equal this, we have to do series addition, meaning that we pick a constant, we pick a particular current, okay? For instance, current between 0 and I. Okay? So the corresponding voltage, or the voltage contribution of this guy is 0. The voltage contribution of this guy is also 0. Therefore, whenever the current is between 0 and I, the voltage, corresponding voltage is 0. Okay, if you pick something a little bit larger, the voltage contribution of this guy is still 0. The voltage contribution of this guy is this amount, okay? And then the overall voltage will be that amount. And likewise, if you go to negative currents, the voltage contribution of this guy is 0, the voltage contribution of this guy is this much, therefore the overall voltage in the original curve is this much. Hence what we're talking about is, we're talking about series addition. Okay. Okay. Now series addition means that we're going to figure out one port that generates this curve, and we're going to figure out one port that generates that curve, and then we're going to add those two one port in series addition. Okay, so let's call this curve 1, and let's call this curve 2. Now, we're already familiar with this shape from our previous lecture. In other words, we know that this curve can be generated by this topology, a diode connected in parallel with the resistor. The resistance of the resistor is R1. R1 plus minus V, and this current is R. And now the question is, how about 2? Okay, 2 is more or less similar to 1, but it has the complication that the breakpoint is not at the origin, but it's a simple complication that we can overcome. But for the sake of completeness, let's decompose this curve into further subcurves. Okay, we can write 2 equals this curve here, with slope 1 over R2, this is the origin, and what you do is, you take this curve and lift everything up by I units, okay? And lifting up, okay, going in the vertical direction means that we're adding a constant source, well, or it can be realized by adding a constant current source in parallel. Okay. So this, therefore, if you want to lift everything up by I units, what you do is you connect to this one port, whatever it is, in parallel, a constant current source that provides a current of I units. Okay. Let's call this curve 3. Let's call this curve 4. Now, 3 can be realized by, note that 3 looks very much like 1. The only thing is, it's 1 is the reflection of the other with respect to the origin, well, modulo the slopes. Therefore, 3 can be generated by same topology here, only difference being that the diode is pointing up now. Okay, and this is R2. Plus minus V, and this is R. And 4 is just a current source, I plus minus V. Therefore, at this point we know all the sub-1 ports corresponding to our sub-IV characteristics or sub-IV curves. What remains is just combine the pieces bottom out. Okay. So let's first combine 3 and 4, obtain 2, and 1 is here, and finally we're going to add 1 and 2 in series to obtain the 1 port corresponding to this ID curve. Okay. So let's do that. So, 2 can be realized by 3 connected in parallel with 4. 3 and 4 here on the board. So what we have is okay. This is I, this is R2, this is I, this is plus. That's 2. Okay, this curve, and we have 1 here, and 1 and 2, they're connected in series, therefore finally 1 connected in series with 2 yields okay, this is 1 with R1, and here we have 2. And this can be one way to realize the ID characteristics of that will give the original ID characteristics. Plus minus V, and here is the current. So this is a possible answer. Okay, we can come up with another design, possibly a better design from some point of view, that will still generate the same ID characteristics as this 1 port here. Okay, now let's see another design example. So we have this ID characteristics again with 2 breakpoints. Here we have one discontinuity at the slope, and here we have another discontinuity at the slope. Here the slope here is given to be 6 moles, and here the same 6 moles. Okay, and between -2 and 2 volts, the slope is half. Okay, that is 12 over 4, we're talking about 3 moles of slope. Okay, so let's figure out a 1 port that contains diodes, constant sources, and LTI resistors that would generate this ID characteristics. Okay, so let's begin by decomposing. So what we do is, in synthesis, one way to go is we decompose the possibly a little bit sophisticated curve, a complicated curve, into simpler subcurves, and be careful about whether to add them in series or parallel. Okay, and then try to recognize those simpler curves. If you don't recognize those simpler curves, and by recognize I mean whether you know a 1 port that will generate the particular ID characteristics. So if you don't recognize those particular subcurves, what you do is you decompose them further until at some point you recognize the one port, and then once everything is recognized, what you do is you construct from bottom to top to generate one port, which would in turn generate this IV characteristics. Okay, so let's begin by our decomposing. Okay, so here is one way. This can be written as a constant current source at 6 ends connected in parallel with this symmetric curve. 0, 2, minus 2 slope, 6 moles slope, 6 moles, and here in between slope is 3 moles. Okay, connecting in parallel means we're lifting everything up by 6 units. Okay. Now we could have do another decomposition. We could have say, okay, this is okay, connected in series with minus 2 volts. Okay, you can, in this case, what you do is you shift everything to the left by 2 units, and this would correspond to a minus 2 volt voltage source, and this 2 would be a valid decomposition. Okay, so what I'm trying to say is this way of decomposing, the way of decomposing is not unique. There are many different ways that you can decompose. Anyway, so this we recognize immediately. This is a 6 amp current source. Okay. Whereas this one, it requires a little bit more work because we don't recognize it directly. So we have to decompose this thing further into simpler curves. Okay. So let's call this 1. Let's call this 2. And this, the original curve equals 1 connected in parallel with 2. We know what 1 is, so we have to now figure out a possible 1 port that will generate 2. Now 2 can be written as the following summation. We have, and here things are flat, the volts I x 0 minus 2, slope is 3 moles, slope is 3 moles. Okay. And then the volt I and if you connect this curve and that curve in parallel, what you obtain is, it's not difficult to see what you obtain is the curve number 2. Now this we immediately recognize, that's a 1/3 ohm LTI resistor, or 3 moles LTI resistor. Okay? So let's call this 3. Let's call this 4. And we know what 4 is. It's a 3 mole resistor. Okay. Now what remains is, how about IV characteristics number 3. Okay. Now some of you may have something in mind that would generate this IV characteristics, but suppose that we don't recognize this curve directly. So one way to go is we decompose this thing further. Okay, so let's do that. Let's further decompose 3. 3 can be decomposed into 3 moles V, I, N, and minus 2, 3 moles M. Okay, and the connection in is parallel. Okay, if you add that in parallel, then what your gain is the curve 3. Now, the curves are becoming simpler and simpler. Now, one nice thing about these two curves is that one is the reflection of the other with respect to the origin. Therefore, if you can figure out the one port for this guy, then the one port for this guy would simply be that one port where the nodes, where the terminals are slapped. Okay? So, in a sense, this component and this component, they're the same component, but when you connect them, you have to be careful. Okay, you connect them in the reverse order. Okay, so let's call this 5, and let's call this 6. Okay. Now, 5 is something that's shifted 2 units to the right, and shifting 2 units to the right means whatever that something is, you connect in series to it a voltage source. Okay, so 5 therefore equals this guy 0, 3 moles connected in series with 0 V volt and okay, this thing. Okay, 2 volts. This we immediately recognize as battery plus minus 2 volts. And this 2 we also, from our previous lecture, know at this point what it is. It's an LTI resistor connected in series with a diode. 3 moles and an ideal diode. Okay. And therefore this connected in series with 2 volt battery gives us this IV curve, and this IV curve is the symmetric of this with respect, or reflection of this with respect to the origin. Therefore, combine this and that in series and reverse it 180 degrees, and it gives you this IV curve. Okay. So 6 is the reflection of 5 with respect to the origin. Okay, hence this thing can be realized by diode is pointing up and the polarity of 2 volts is reversed. 3 moles and minus plus 2 volts. Okay. And now we're done. We have figured out every sub-curve's corresponding one port. What remains is to combine all those one ports. Be careful about whether the combination is through parallel addition or series addition. Okay. Now we glue the pieces together. Pieces together. So we have 5 and 6. In parallel, okay, 5 and 6, and that gives us 3. And 3 was connected in parallel with 3 more resistor. So this is 3 mohs, this is 3 mohs, minus plus 2 volts, plus minus 2 volts. This 5 and 6, this is 3, and 3 is in parallel with 4. 4 was this 3 more LTI resistor, and that's 2. And 2 was in parallel with 1, and 1 was a 6 amp current source. Okay, and therefore our design is correct. Plus minus V, and here this is the current.